So in the fourth session of the strength of material interview section, let's start about discussion about load deflection diagram versus the stress strain diagram. So what does this diagram tell about the areas? So basically, to have the curves for both the diagrams, we need to test the material under the uh, uniform testing method, universal testing method using the jaw method. So in this thing, the material is pulled in both sides. This is basically a tensile test, and from this we will get the tensile stress of this is the engineering stress, because we are using the actual area, actual length of the material. Okay, so in this test, using UTM, it's always the gradual loading, the static loading basically. So from this thing, we will get the load deflection curve as well as the stress strain curve. So this is the gradual loading graphs. From this thing you will see that, so in this thing, is it F or X, which one is the input here? In this thing, the X is the deflection is the input and this is the output, because if it is the input it will come here. This is the input, this is the output, and this F is not, it's not the applied force, but it is the resistance force. So always from the spring thing, you can always notify that always the force is applied here down, and after deflection happens, and due to the resistance inside inside the spring, the resistance force is created, means it's induced inside this. So this means this one is the induced resistance force. Okay, so that's why it is in the y-axis. It is the always axis in x-axis it is the input, y-axis is the output. Okay, that's what is written here. So from this area we will get the strain energy which is loaded during the elongation period. This is energy stored in the material during the process. It's called strain energy, and that is half Fx. It's actually work also. Same thing happens here until uh, until the elastic range. It is basically modulus of resilience, and the whole thing with the plasticity is called modulus of plasticity or toughness. So this area also refers the strain energy loaded inside the object. So this is the engineering strain, engineering strain and engineering stress. Okay, so the area is half sigma epsilon, that is uh, sigma squared by 2e, that is, and AE is the strain energy stored in the elastic region per unit volume. Okay, this is per unit volume, and it is, this one is completely the strain energy loaded in the whole body, the volume of the body. Okay, so this Fx curve depends on the loading, type of loading, gradual, sudden or impact loading, but the stress strain curve is the property of the material and it doesn't depend upon the loading condition. Okay, next one is the resilience and toughness. Resilience, this is resilience which is until the elastic region, and when load is applied it goes to some deformation, and after the load is released it comes back to it. And this is the ductile region, it shows the whole toughness part, toughness region, this is the whole toughness region is that. So in resilience it is basically, it stores the elastic strain energy, and but this stores the total strain energy. And in resilience, materials used are basically cast iron, which has a high carbon content, and here they use only mild steel which has a low carbon content. So basically special steels or alloy steels are used. For example, the springs are used under the resilience period, because spring has resilience mode because it takes only short small loads, and they are used for specific applications only. They doesn't work under applications which has long loadings, such that the spring goes into the plastification or has a permanent deformation. So we don't use the spring in that applications. But if you want to use the applications in which there is a long periodic loading or high impact loading, in that case we use anvil kind of material, in which the material is hammered or stamped such that the material is made to absorb high energy, high stress energy and impact loads. And in this case their fracture point is far away, and they have very high absorption rate, energy absorption rate. Okay, so there are types of loading, and what are the stressing curve as well as the load deflection curves. So for the general gradual loading, it is also called static loading. As we see, this is the area, and this is the strain energy load in this graph, and the same goes to the strain curve. This is the energy per unit volume. Okay, so next goes to the sudden loading, in which load is applied suddenly. So this is the loading deflection curve, and this is the stress strain curve, which doesn't depend upon the loading conditions. So from this curve we will get the area as this, which is quite different from this one because the area is different. So same goes to the but here the energy is same. When we equate it, we will see that the energy, the area of this area and this area both are same. So when we equate it, we will see that the stress in this case is twice the static stress. This is static stress. Static stress means the gradual loading stress. This happens because of the sudden loading. Okay, so this 2 is called the impact factor. Impact factor is nothing but a factor which is multiplied to the static stress. Okay, so here in this case it is only 2. So next go to the third kind of loading, which is called impact loading. Impact loading is nothing but when the object is released and this creates some kind of deformation in this plate itself. So in such cases the loading deflection curve is similar to the sudden thing, and the stress and strain curve is same. But the thing is that in this case the potential energy, when we drop this object here from here to here, the potential energy is F times H plus X. H plus X, it is created, and as we know the strain energy of this curve is this one per unit volume, per unit volume, and when we calculate the total strain energy, it is volume is multiplied. So that means the potential energy and the strain energy are equal basically. So when we equate this, we will get the stress as this is a kind of expression. So we will, when we separate this, we will see that the stress is equal to static stress times the impact factor, and impact factor is nothing but this. Then the impact factor is simplified to get such an expression, and here the gamma delta x is nothing but static displacement. Okay, so now let's move to the analysis of the center of mass or center of gravity versus the centroid. Centroid is nothing but a geometrical center of a certain shape that is a 2D plane body, and while the center of gravity or center of mass is it is assumption that the entire mass of the body is concentrated at a single point. It is in the 3D real body. For example, we have a homogeneous body. The center of gravity is along the diagonals. For inhomogeneous, it will differ because, for example, if there is a wood and there is iron, the center of gravity will be in iron. Okay. So if you want to calculate the centroid for the L shape, you will see that we will divide the body in a simple manner, such that we will see the center of gravity is here. Sorry, centroid is here, for centroid is here, and then we will calculate the centroid as with such an expression. Okay. So if we have many such simple bodies, then we use the summations, and if we have a curved kind of body, and for this thing the curve expression is y is equal to kx square. In that kind of cases, we will use the integration method. So what we will do is find the area, and we have such an expression, and from the same thing we will replace the area function, area expression with this expressions, and we will integrate it to find the centroid of the curved surfaces. Okay, thank you.